I'm going to try and find an equation that will, or derive one, that will show us how energy is related. Like for example, if you're driving your car at 50 miles per hour, you want to pass a car, you step on the gas and it goes now 70 miles per hour. There's a change in the kinetic energy. What made that change in the kinetic energy? That's your engine. There's work done by your engine to make your car goes from 50 to 70, so you can pass that car now. If you remember, Newton's second law says F equals ma. Remember that one?
What's the word after work energy? The record.
Theorem.
Theorem.
Yep. F equals ma. Remember that one? From this equation, you can write the acceleration as what? F over m. Let's take another equation from the early chapters, and that says V final equals what? Squared, V initial squared, plus 2a times delta x, right? Let's use d instead of delta x, distance, you know? The distance traveled, or delta x. Let me use d in place of that. Remember that equation? Equation number 5, V final squared equals V initial squared plus 2a delta x, the distance traveled. I decided to use d instead of delta x. Now let me do a substitution. Replace a here with f over m. See it? Let's do that substitution. And let me play with this. This becomes v squared equals v0 squared plus, I can write that 2 over m. I'll make it like this. How about 2 times f times d over m. And what is f times d? What did we say earlier today? F times d equals what? The work done is what? Isn't that f times d? And let me bring that v0 squared to this side. So v final squared minus v0 squared equals 2 times w over m. I don't like fractions. To get rid of that, I'm going to multiply the entire equation with m. That means I'm going to multiply this side by m, and I'm going to multiply this side by m to get rid of the fractions. So 2 times w equals, I'm almost done deriving the equation, mv final squared minus mv initial squared. And to solve for w, I'm going to divide each one of these by what? By 2? Or multiply by a half. Doesn't really matter. Dividing by 2 the same as multiplication by a half. So what is the work done? It's really 1/2 mv squared minus 1/2 mv initial squared. The topic is kinetic energy. This is actually what kinetic energy. Kinetic energy is defined as 1/2 mv squared. Our book uses K. Sometimes I write KE for kinetic energy. I'm guilty of using that. But our book uses just K. It's 1/2 the mass times the velocity squared. That's called the kinetic energy. Kinetic because something is moving. If a car is moving, it has kinetic energy. You know it has kinetic energy because if it hits another car, it's going to dent it. It has a lot of energy in it. And that amount of energy is the mass of the car times the velocity squared divided by 2, or 1/2 that number. Now, if you want to get your car to go from 50 to 60 miles per hour, how much work is done by you? That is the change in the kinetic energy. How much kinetic energy you initially had. Now you stepped on the gas, now you're going faster, you're going to have more kinetic energy. The difference between them is the work done. So work is actually labeled as the change, delta means change, in kinetic energy. Yep. The change in kinetic energy, which is 1/2 mv squared minus 1/2 mv0 squared. We'll take a few examples on that with these equations. So these are the two equations that I'm going to be using. The work done is the change in kinetic energy, or 1/2 mv final square minus 1/2 mv initial. The other one you should know, the kinetic energy equals 1/2 mv squared. We know that from earlier today. So far these are the equations. Now let me take an example here. A truck moving at 15, here we go. We have a truck moving at 15 meters per second and has a kinetic energy, K, kinetic energy equals 4.2 times 10 to the 5 joules.
10 to the 5?
10 to the 5th, yes. Question A, what is the mass of the truck? And question B, if the speed is doubled, comma, by what factor is the kinetic energy changed by? If the speed is doubled, by what factor does the kinetic energy change? Well, let's look at the first one. We know the mass. We don't know the mass of the truck. We're looking for it, right? The mass is unknown. We know the velocity of the truck, which is what? 15 meters per second. We know the kinetic energy, which is 4.2 times 10 to the 5. Is there an equation that ties these things together? We have kinetic energy equals what? 1/2 mv squared. Remember that? 2 minutes ago. Do we know the kinetic energy? 4.2 times 10 to the 5 equals 1/2. The mass is unknown. The velocity is 15. You got to square it. 15 squares 225. Bless you.
Thank you.
0.5 times m times 225. 0.5 times 225, it's 112.5. M equals 4.2 times 10 to the 5th. What is the mass of the truck? 4.2 to the power of 5 divided by 112.5. And I get 3733. Is that what you got? Kilogram. If you're going to use two significant digits, that's 3.700 or times 10. I changed my mind halfway through. It's 3,700, or you can write that 3.7 times 10 to the third kilogram. You can do it either way, both two significant digits. Now if we double that, it says if the speed doubles by what factor? I will say 4. Why? Because that's going to be 2 times that number. When you square the 2, what's the factor? 4, because that doesn't change and that doesn't change. But I'll show you the math. Let's double that speed. So now what is the kinetic energy if the speed is doubled? 1/2. We know what the mass is, 3733. And now the speed is doubling. Instead of 15 becomes what? 30 squared. Square the 30 first, order of operations, times 3733 times 0.5. The kinetic energy, which is what? 1679850 joules. Let's compare it to that number. So what is 1679850 divided by 4.2 times 10 to the 5? Let's see if that number equals to 4. $3.9996. So what is that? 4 times. And again, if you double that number, you write 2 times that. When you square the 2, it becomes 4. And that's why, actually, if the speed is doubled, the energy changes by a factor of 4. When you go in 5 miles per hour and you hit a car, you're not going to put as much damage as you go in 10 miles per hour. 50 miles per hour versus 100, the damage by 100 miles per hour is a lot worse than going 50 miles per hour. Let's try another one. There we go. Example, to accelerate a certain car from rest. So we have a car, initial velocity equals 0, at rest, accelerate that to a speed, go ahead, pick a number. What is it? 5. A speed of 5 meters per second. How much work is required for this? We'll call it W1. And my next question, would that be the same amount of work as to get the car from 5 meters per second to now double that? 10. We'll call that work 2. So to go from 0 to 5, how much energy is required? And to go from 5 to 10, how much energy is required? And do you think these values will be the same? Well, let's look at the first case. To go from 0 to 5 meters per second, how much energy or work is required? You see me the word work? Because work is changing kinetic energy. So the work required, that's by the engine, to go from 0 to 5 meters per second. Let's find out how much work is required. That's W1. We say work is change in kinetic energy, which means 1/2 the mass of the final speed squared velocity minus 1/2 the mass, the initial velocity squared. Now, I never gave you a mass for the car. We can leave the answer in terms of m, or we can use a number. You want to use a number instead? Let's pick a mass for the car. 1,000 kilogram. £2,200. That's what an average car is. Honda Accord, Toyota Camry, about 2,200 pounds. You know. So let's see how much work is required. So the work to gross will be 1/2 the mass, which is 1,000. What is the final velocity for the first case? Final velocity of the car from 0 to 5. So the final velocity is 5, and you're going to square that. Minus 1/2 the mass, which is 1,000, times the initial velocity, which is 0. Is it 12,500 joules, I think? $12,500. Let's see the work required now. To go from 5 to 10 meters per second. Again, work is change in the kinetic energy, which is 1/2 mv final squared minus 1/2 mv initial squared. The mass is what? 1,000. Final velocity is 10 squared minus 1/2 1,000 times the initial velocity, which is 5 squared. And look how much work is required. 37,500 joules. A lot more joules. Almost, what is that, divided by 1250? 3 times that amount. So the faster you're going, actually, the more work you're going to need to get the car to move faster. And the reason, because you're squaring that number. You're going from 55 to 65 or 55 to 60. I can tell you what that number to go from 55 to 60. I'll just do it on my calculator. Ready for that number? From 55 to 60 will require 287,500 joules. 287,500 joules. Now, all these problems, I'm assuming it's actually you're on a flat surface, because if the surface is not really flat, then that changes. I'm assuming the force is constant. Is the force always constant? The answer is really no, not always constant. There are cases where the force is not constant. Like what? How about a spring? The more you stretch it, what happened to that force? The more pulling on it, right? So as you come closer and closer and closer, that force starts to decrease. So and there are some cases where the force is not constant. But we're dealing here with this section with a constant force.